Okay, should we get started? So, welcome everyone. Bouma. I get to host this beginning session for our symposium, which I have co-organized with my colleague Polina Golan from MIT, and with significant assistance from Jacqueline Namadi and from Martin Villiger and from Stephanie Nam, all at MGH. Thank them all for their participation. I'm just going to share a couple of slides here. So yeah, welcome to the Machine Learning and OCT Symposium. This is a virtual symposium, obviously, and this is our first time hosting a virtual symposium. I think that we have a good recipe and a good agenda for you today, but we're going to go over some of the details about how we intend to foster interactions and discussions in a few minutes. And I just wanted to make a few quick remarks. We're hosting this symposium as part of our NIBIB P41 Research Center, which we call the Center for Biomedical OCT Research and Translation, and the website is octresearch.org. One of our missions is, in addition to research, obviously, is to foster education and dissemination of OCT technology. And in addition to hosting symposia and workshops, we also foster the dissemination of OCT technology by providing access to software on our website for signal processing and image processing, but also the designs of probes, the designs of systems, and the assistance in making probes and systems. We have the opportunity for outside investigators to come and to learn about how to make catheters, for example, or how to make lasers, how to use those, how to calibrate those, how to make systems function. And we also have an initiative where we provide access to imaging systems, either inside our facility or in some cases by fielding systems to collaborative sites. And typical objectives for those types of initiatives would be to investigate new potential applications for OCT imaging, or to, for example, obtain preliminary data to support research proposals. So if you're interested in any of those resources, please see our website, and please feel free to contact either Jacqueline Namadi or myself. So the objectives for today's symposium include to explore the interface between machine learning and OCT. And there are two factors which led us to this objective at this time. And those include that the fact that machine learning obviously is growing at an incredible rate, and its capabilities to address a wide spectrum of applications and challenges in biomedical imaging have grown incredibly. And at the same time, OCT has progressed to a more mature field to the point where we have very large data sets in particular three clinical fields: in ophthalmology, cardiology, and gastroenterology, but also in preclinical imaging. So the data sets are significant enough now to underpin some of the important methods in machine learning. And just as examples of that opportunity, there have been recently two machine learning trained algorithms that have been developed for OCT image analysis and interpretation as commercial devices and inclusion in medical devices, one in gastroenterology and one in cardiology. So it's a pretty exciting time, and we felt like it was a perfect opportunity for us to base a symposium. And we hope that we have members of both communities, and perhaps members of those communities may not, for example, in machine learning, know that much about OCT and vice versa. So we've designed the program to include an overview in our beginning session on machine learning principles and concepts, where it stands as a field, but also on OCT and what are the principles of OCT, very briefly, as they pertain to machine learning opportunities. The further sessions through the rest of the day are more specific on topics where folks have started to work at the interface between machine learning and OCT. So I think that we are all set to use Hop-In effectively, and I would like to take this opportunity to welcome our first speaker, Daniel Rueckert, who was very kind to agree to join us and to provide an introduction to machine learning in the context of what we envision the day to include. Daniel is a professor of visual information processing at Imperial College in London. He's joining us remotely. He heads the biomedical imaging analysis group there. He did his PhD in computer science at Imperial College and postdoc work in the Division of Radiological Sciences and Medical Engineering at King's College, where he worked on non-rigid registration algorithms that have been commercialized subsequently. He currently is an associate editor of IEEE Transactions on Medical Imaging and is a fellow of the Royal Academy of Engineering. So welcome, Daniel.
Thank you very much. I hope you can hear me well, and I hope you can also see my slides.
Yes.
Thanks very much for the kind introduction and for the invitation to give a talk today. And I've been asked to give a bit of a tutorial talk on the topic of machine learning in medical imaging. And I know you are very much focused on OCT. Unfortunately, you're not going to see many OCT images in this talk, but I'm sure you will see plenty of later on. So I'm going to start and try to highlight some of the open challenges of machine learning and imaging, as well as perhaps what might be really some of the things people might want to focus on in the future. So I think many of you will have seen headlines such as what you see here on how AI and in particular machine learning is going to transform many aspects of medicine. And I think imaging is quite often here at the forefront, because I suspect that imaging really is where I think AI has made many of the advances so far. Now, there's also a lot of hype in this area, and those of you who have a bit of experience with machine learning will know Jeff Hinton, who won the Turing Award 2 years ago. And the Turing Award in computer science is effectively what we have as our Nobel Prize, so the highest award. And he made a quite bold statement a couple of years ago, saying we should stop training radiologists now. And of course, if you ask a radiologist, they will tell you something quite different. And actually, I have to agree with Curtis Langlotz, who said in the same year as a response, basically, to the question, will AI replace radiologists? I think the answer is no. But radiologists who do AI will replace those who don't. And I think that's a very good summary, very much sort of, I think, basically bringing it to the point what AI has to offer in the field. It's not going to replace us humans, but it's going to transform how we work. So I wanted to give you sort of a bit of an overview here, and I think I'll try to make the screen a bit bigger. I hope you see this quite nicely now.
Yes.
On that AI, quite often we think about AI being used for diagnosis and prediction, and really the bit which is important for the patient. But there's a lot of potential for AI through the entire imaging pipeline, from how you acquire the images, how you process the images, for example, improve the resolution, denoise it, how we can then interpret quantitative information from the images, and so on. So I think what I wanted to do is highlight really that AI is more than just trying to automate a diagnosis task. So I'll come back to a few of those examples as we go along. But I also wanted to just give you a very, very quick summary of many of the technologies I'm going to show you. And the key message I want to bring across here is that actually much of what we do in machine learning these days is actually not very new. So the basic building block, the perceptron, I guess is over 50 years old, and it's still what's driving neural networks. The neocognitron, which is basically the earliest idea of a convolutional neural network, again, is 40 years old. The backpropagation algorithm, how we train neural networks, also very well known, very well understood. What's really made a difference, I guess, was Jan LeCun's work on convolutional neural networks, for which he, with Hinton, won the ACM Turing Award, which really showed the first working system which could be efficiently trained to recognize handwritten digits in images. And really, this was the first time that actually all these basic building blocks had been put together and made into a working system. And more recently, of course, the introduction of GPUs has really transformed how we can scale this up to build very, very deep networks. But I guess really the main point is the basic building blocks have been around for quite a while. So really all the math which you in principle need for doing what I will show you today is effectively on this one slide, and really shows you what computation a neuron performs in terms of computing a linear sum of inputs, which is then passed through a nonlinear activation function. We have to define a loss function, which tells us what we actually want to optimize, and then we typically minimize our loss function via gradient descent. So if you're an engineering student or computer science student, I guess all of these things will be fairly standard and very easy to understand. So given those basic building blocks, what type of networks, neural networks can you build for imaging? Well, the first network I'm going to show you here is a very simple neural network which takes images in, passes them through convolutional layers, and simply performs a classification task. So we have per image, we have one output or a categorical output, for example, whether this image contains cats or dogs. Now, this is simply a neural network which can be trained with backpropagation, but it's probably not necessarily in imaging something we always want to do. Quite often we want to, for example, segment our images. Many of you will be familiar with this task where we want to segment images. And you can view this as a very similar problem where we take a neural network, which takes an image as input. And now instead of making one prediction for the image, we're going to make a dense prediction. So we're going to try to predict for every pixel a label. And so the input and the output effectively have the same size. And we can do this segmentation effectively by viewing this as an image-to-image translation task. So we have a network which encodes our image into an abstract bit of information and then decodes it again to try to make a dense prediction. And there are a couple of different architectures you can use for this. Probably the UNet from Olaf Ronneberger is probably by far the most well-known paper. I think it has over 20 or 30,000 citations by now. So this is sort of the standard approach for doing this. And the other network you can also use, which is also very, very well known and quite often referenced, is a so-called generative adversarial network, where you effectively have two networks which compete against each other. You have a generator network which tries to take a noise vector and transforms that noise vector through a neural network into an image. And that image is then fed into a second neural network called the discriminator network, which tries to detect whether this is a synthetic image or comes from your training data, i.e. this top branch in this network. So here the generator tries to learn to generate as realistic images as possible, and the discriminator tries to detect whether you're trying to fool it by identifying whether the data is real or synthetic. And we'll see a couple of examples of this later on. So let me show you a first example of what you can do with these type of networks. So let's assume you're doing MR imaging, and I know Florian Noll is speaking after me, so I'll be very brief on this. In MR imaging, we acquire the case-based data, we apply a Fourier transform to get the image data or to reconstruct the image. And this is a slow process. So if we want to accelerate our image acquisition, we might, for example, decide we're going to acquire only a quarter of the data. If we then would reconstruct the data with a Fourier transform, we get all sorts of aliasing artifacts. So here, the machine learning problem would be, can we try to take the image with artifacts and remove the artifacts and learn how to reconstruct a clean image from undersampled data. Now, you can view this effectively as an image-to-image translation task. I take the image with corruption and I try to transform it into an image without corruption. Now, this is a very, very simplified view, and I'm sure Florian will tell you that this is not a very good view to take, but for the purposes of this talk, I'm just going to leave it at this. And there are many tricks you should play if you're doing this, but this is in a nutshell what we're trying to do. And here's an example of what you can actually do with this. On the left-hand side, you see an MR image of the heart, undersampled by a factor of 6. So it looks very, very bad. On the right-hand side, you see the ground truth image, fully sampled and then reconstructed. And in the middle, you see what the deep learning approach would do if you try to apply this to the data on the left-hand side. And you can hopefully see that this is an almost perfect reconstruction. You see almost no differences between the ground truth and the undersampled data, which has been reconstructed with machine learning, but this is 6 times faster. So the patient has to lie in the scanner for only a 1/6 of the time. So that's a significant improvement. Now, I can use the same type of network as I've shown you before to do image segmentation. Here, I'm effectively going to do the same thing, except that my output of the network is not going to be an image of ordinal values, but here it's going to be an image of categorical labels, i.e. the segmentation labels. We have, for example, in our group, worked a lot with trying to apply this to the heart. You can see that you can, for example, segment the heart very nicely, even in dynamic sequences. But I think probably the biggest advantage of these machine learning approaches is that I can use the same approach to segment different structures in different types of images. The only thing I really need is different training data. So basically, these different examples you see here, they all use the same segmentation algorithm or the same segmentation network, but they're just trained with different images and different label maps. And I think that's one of the big advantages, that we can actually be much more flexible in how we design our applications. We just need the training data. I'm also going to show you quickly an example of how you can do image recognition or image classification. We have done this in an example where we want to take ultrasound images and identify standard view planes. For example, in fetal ultrasound, you would like to recognize a certain set of scan planes. And here you now use a network which effectively performs classification. And actually, it turns out that these networks are very, very fast. They can operate almost in real time, well, actually in real time. And I'm going to show you an example of, for example, a workstation where we have such a plugin where a neural network recognizes as the sonographer scans the patient, automatically these view planes, and populates the view planes the sonographer has to cover. And there's a neural network here running in the back in real time and automatically identifying the correct view planes and capturing those. So the final example before I come to some of the problems is I wanted to also show you something on, for example, using a neural network to predict, for example, outcome for patients or diagnose patients. And I've shown you a lot of examples using the heart as an exemplar, and I'm going to stick with that. Here is an example where we, for example, have segmented the heart in different time frames, but we can also track the motion of the heart using these neural networks. And when you track the motion of the heart, you can actually reconstruct for every point on the surface of the heart, and this here is the right ventricle of the heart. You can track the motion of the heart, and this is what's represented by these spaghettis which come out of the surface of the heart. So now we have the structure of the heart and we have the motion of the heart. Can we diagnose whether patients with a particular disease, in this particular case here, pulmonary hypertension, right ventricular pulmonary hypertension, whether they have good survival or poor survival? And what you see on the left-hand side is a neural network which takes this data I've just shown you as input and then compresses this data, which is indicated by these few nodes in the middle, and then decompresses this data. This is called what we call an autoencoder. So we encode the data and we decode the data, and by having this bottleneck in the middle, we effectively force the network to learn the salient information in the data. But at the same time, we use this salient representation to try to make predictions about whether the patient has poor survival or good survival. And it turns out that if we use this for this prediction, then we can actually separate these two groups much better than we could when we use conventional MR parameters. So this also shows you that you can use these networks also for diagnosis. Now, I've shown you a lot of examples where things seem to work very well. I also want to show you some of the problems which are out there. So one of the problems is that many of these systems are effectively black boxes. So if you, for example, do this diagnosis I've just shown you, and you want to separate, for example, two groups of patients, you have this black box system, you represent it by a neural network, but that neural network is potentially quite complex, even though all the individual units in the network are very simple mathematical expressions. Plugging them all together is sometimes very challenging to unravel. If I do segmentation, I do effectively the same thing, or image reconstruction. I have this black box system represented by a neural network, and that makes it sometimes very difficult to interpret what's going on. Now, why is it so difficult to interpret this? Well, if you think about this, effectively this machinery you're using to do the segmentation is a machine which has lots of knobs you can turn, and the training of the neural network finds out what's the optimal position of these knobs, of these weights in the network. Now you just have millions and millions of them, and the interaction of these are very hard to understand. So this is potentially a problem and something you need to keep in mind, especially if you don't do a task such as segmentation, where it's easy for a expert to afterwards look at the images and decide, yeah, you got it right or you got it wrong. So if we also think about what the real challenges are, then in Europe we have a set of guidelines which people sort of often cite for defining whether an AI system is trustworthy. And I'm going to focus very briefly on some of these more technical aspects of this, and I wanted to show you what some of the issues or open questions in this context are. So the first thing is, if we want to really build systems which are interpretable, that's not necessarily the same thing as building systems which are fair or accountable, or, for example, ensure causality or privacy. So interpretability is very, very useful, but for example, just because I have a system which is fair, it doesn't mean it's actually interpretable. So let me show you why sometimes this can be a problem if your system is not interpretable. This is from a paper which is a couple of years ago, which showed quite nicely that when you train neural networks with lots of different images, they were quite easy to fool. And the reason why they were easy to fool is because actually they didn't really recognize what's in the image. They seemed to recognize that there was at the left bottom of the image, there was a tag with some text written, and they actually learned what was written in this text. So if you then instead of putting a car into the image, it would still recognize it as a horse because it had the same text which it had learned to recognize. And obviously, this is not something you would immediately notice when you look at this. To the human, it's probably you probably tend to ignore the text because you have some prior information what might be really interesting in the image. So this interpretability is also very useful for debugging your machine learning model if you, for example, don't figure out why it works. And people have shown that, for example, neural networks seem to really focus much more on texture than they do on shape. So easy to fool a neural network into thinking this is an elephant on the right-hand side, even if it really looks like an image of a cat, because it really doesn't know the concept of shape. It seems to just focus on the texture. What we typically do to make our systems more robust is that we augment our training data sets with lots of variations of the data. So what you see here is that if I have a single image, I can try to generate lots of variations of that image. And by doing so, I make my machine learning system more robust. Here's, for example, an example where people have proposed that in order to really focus a neural network on learning shapes rather than textures, why don't I generate lots of different styles of textures for the same shape? And I'm telling the network that all of this is the same shape. And people have shown that this type of approach can work, but it's quite hard work to generate all this artificial data. The other thing which I wanted to show is that it's also sometimes quite easy to fool your neural network. So this is a very famous example from the literature where this image is very clearly labeled as a panda by a human and by a neural network. If I add a very, very small amount of noise to this image, and you can see from the coefficient that this noise is extremely small, so that actually the resulting image looks to the human visually as almost identical to the image on the left, then I can fool my neural network into thinking that this is a completely different object, in this particular case, a gibbon. So this is what's called adversarial attacks, because I'm actually looking for this pattern in the middle to try to fool my neural network on purpose. Good. The last two examples on open challenges I want to briefly show you is how do we build neural networks that generalize well? Because quite often you will sit in your lab and you build your training, your neural network, you train it, you've tested it in the lab, it all worked well, and then you put it into the clinic, and suddenly in the clinic you realize that actually, you know what, hang on, my data looks a bit more diverse than what I had in my training, and nothing really works anymore. So it's quite important to make sure that you have data which is quite representative of what you actually want to test on. Now the challenge for this is sometimes actually your data might be different for different reasons. So for example, I assume this is also the case in OCT imaging, I might, for example, have data from one type of scanner, and I've trained my neural network to find me a good separation between my two classes. And now I'm switching from one OCT machine to another OCT machine, and that produces data which has a slightly different distribution. And now you see that the blue line I've learned first actually works for the blue points, but doesn't really work for the green points. Ideally, I should have learned a model which would have separated the data like this. This would basically work well for my OCT data from scanner A and from scanner B. But this is very hard to do, and also you would need to have training data for both the source domain and the target domain to do this. So this is something well known called the domain shift problem. And you can deal with this to some degree using adversarial learning. The idea of adversarial learning is that you learn a domain classifier which tells you whether data comes from one domain or the other domain, i.e. from one OCT scanner or the other OCT scanner, and that you're going to try to minimize the accuracy of that domain classifier. Now you might say, hang on, this seems crazy. Why would I minimize the accuracy of this? Well, if you minimize the accuracy of this, you're basically learning something which is domain invariant. Let me show you this in a very simple example. Let's assume I want to segment images of the heart, and I have data coming from 2 different scanners, but I've only labeled data from scanner A. So I train my neural network as I've shown you before. It actually does very nicely, a very good job. But now I also plug in data from scanner B. But I don't have training data from scanner B to tell me how the segmentation should look like. Well, what I can do is I can add this adversarial branch in the middle of the network, which tries to classify whether the data comes from scanner A or B. This is the so-called discriminator branch. And I'm trying to minimize the accuracy of that discriminator, because that discriminator only uses the features from the bottleneck in the network on the top. If it cannot detect whether the data comes from scanner A or B, then the features I've learned at this bottleneck layer are actually domain invariant, and they can't distinguish between scanner A and B. And that means that my segmentation would effectively perform equally well for the data from scanner A or B. So that's a very useful trick you can use if you don't have labeled data for all your different domains. The final thing I wanted to also highlight is that at least in Europe, there is a lot of debate on how do we ensure that when we in the medical domain use data for training machine learning systems, that we ensure security and privacy. There are many different technical things we can do in this space. We can use federated learning, i.e. distributed learning, but that doesn't necessarily ensure that our data is private. We can use learning with homomorphic encryption or with secure multi-party computation. And I just want to show you one example why this is important from a paper which is coming out next week from our group in Nature Machine Intelligence, where we have shown that when we train models in a distributed fashion using federated learning, if you don't, for example, ensure things such as differential privacy, it is actually possible to reverse engineer from these models the images that were used to train. So on the left hand, on the images on the left hand, on the right hand side, in the left column there, you see some of the images in the training data. In the middle column, you see some of the images which we have reconstructed from the neural networks without knowing really the training data. And if you enforce differential privacy, which is a mathematical tool to ensure that your data is private, you can see in the right-hand column that you can't really reconstruct anything from the data anymore. So data protection is certainly also an issue which is very important, especially in the medical domain. And with that, I want to just come to the end. Probably just say very briefly, at the moment, we have been working very much in a sequential fashion where we do acquisition, reconstruction, analysis, and interpretation of the data. I think in the future in the medical imaging field, we'll probably go to a much more integrated approach where all the different components hopefully interact with each other. We can steer the acquisition. We can dynamically decide whether we have enough data for reconstruction of the images, and so on. So hopefully through AI, we can have a much closer coupling of these different steps. And perhaps what's also important to realize is perhaps we will also be able to make more direct jumps from the data we acquire to the diagnosis. Perhaps we can just have a massive neural network going directly from your MR signal or your OCT signal to the diagnosis. And I think that's a bit further away, but it's an interesting idea for future work. And with that, I want to stop here, acknowledge all our collaborators in our group at Imperial College in London and also at the Technical University of Munich. Thank you very much.
Thank you. That was outstanding. That was just the perfect way to start the day, and gave a great introduction to many important issues in machine learning that I think folks in the OCT community are going to identify a number of different opportunities, but also the importance of some of the cautions that you brought up, because I think we're already starting to see some of these. So that we have a couple of questions in the Q&A. Commenting on the excellence of your talk. Thank you. Could you elaborate on why UNet has become the standard framework for medical imaging?
That's actually a good question. There are actually two very similar network type architectures. One is called fully connected network, FCN, and the other one, the UNet. The UNet was proposed in a medical imaging conference, the FCN in a computer vision conference within the space of 3 months. I think they are almost identical in what they do. And for some reason, the UNet approach has just taken everybody, or has become the de facto standard. And I think the computer vision community and the medical imaging community are very much sort of benchmark driven. And I think at this point, almost nobody dares not to use a UNet, because every reviewer would tell you, why have you not used the UNet as a comparison? So it's a reinforcing system. It is a very good network, which basically computes features at different scales and has skip connections. So I think it has all the right ingredients. So it's a very good model. I can't really tell you exactly why this is really so popular, but it is a very good approach.
Another related question just came up. What do you see as the limitations of the UNet?
So I think one of the limitations are that, and I think you might have the same problem in OCT, is that quite often we want to do things, of course, fully 3D. We don't want to do things in 2D. And you can very easily have, for example, for large medical imaging data sets, let's say you're talking about 512 cubed data, you probably don't have enough GPU memory to fit your models onto a GPU. And that is probably the downside. So there are lots of approaches, also some from our own group, where people have tried to come up with more efficient ways to train these UNets, because effectively they're so memory hungry from their architecture. I would say that's the main limiting factor.
Yeah. Is there a way to estimate the required amount of training data from some metric of problem complexity, for example? I mean, for those in the OCT community, this is a really important issue. When do we have a sufficient data set to attract interest from experts like yourself?
So, well, I think the interest is definitely there from people like us. Whether there's an unambiguous answer to whether you have enough data or not is very, very difficult. So I know so what you typically do is you test how well your model generalizes to unseen data. So you take your data, you split it into a training set, a testing set, and a validation set. And in that validation set, you're trying to, you really show this to the model at the end when you've fully trained it, when you've determined your hyperparameters. And then you can see how well it generalizes to that. And I guess if you then see a significant performance drop compared to what happened during testing and training, then that's typically a hint that you don't have enough data. But the other problem is you typically have machine learning people telling you can never have enough data, correct? I mean, they will always tell you, give me more data and it will work better.
Yeah. Numerous congratulations on the excellence of your talk. Question here. Could you comment on the potential pitfalls in image enhancement and reconstruction, in particular the example that you showed of removing the Fourier transform artifacts of undersampling, that's so relevant in OCT. But how susceptible is that approach to introducing other artifacts or hiding real pathology, for example?
Yeah, that's a very good question, and it's nice to see Jonathan Oakley ask the question. So I know Jonathan from a long time ago. So this is something where people have worried about, but I think there are also approaches. People have also now shown it's probably less of an issue than people think. So we have, for example, shown in our lab, and we've also seen other publications on this, where people have, for example, in the MR case, trained networks with knee images and then reconstructed brain images with it, or completely different structures. And I think that really works because when these networks are trained, they only see relatively small parts of the images, patches from the image. And they learn the structure of patches. They don't really learn the overall anatomical structure in the image. And that seems to be very encouraging. But there is still a debate over whether you can guarantee that you, for example, will not make a small lesion disappear in a reconstruction. And I don't think this is a solved problem yet.
Yeah. We should probably wrap up and move on to the next speaker. Daniel, that was just outstanding. The perfect way to start the day, and thank you so much for participating.
Thank you very much.
Remember to join us in the break session. So if we could have our next speaker, Florian, join us. Florian is an assistant professor in the Department of Radiology at the Grossman School of Medicine at New York University. He heads a technical research and development project in Dan Sodikson's P41, so a sister organization to our own in Boston. In fact, Dan Sodikson was in the Boston community for a number of years, and I knew him while he was there. Florian did his PhD in electrical engineering in Graz in the University of Technology, and postdoc training at that same institution, but also at the New York University in the Department of Radiology. His research includes several projects in the general area of machine learning in medical imaging, but has a focus on data acquisition and image recon methods that improve MRI. So Florian, thank you very much for joining us.
Yeah, thank you very much for your kind introduction. I just wanted to double check, can you actually see my slides now? Because I see only a blank screen or a black screen.
I just see a black screen also. I see your video link and I hear you clearly.
Okay, let me try this because I think I try this again. So you see them now, right?
Perfect.
When I go to presenter mode.
Yeah, maybe it's set up to do a second monitor and you're sharing the first. If you don't go to presenter mode, the slide was very visible anyway. So if you just run it in slide sorter mode, that's probably fine as well.
I'm sorry about that. We tried this in the...
Hi, Florian.
Hey.
Hi. You first have to start the presentation before sharing the screen, I think.
Oh.
So yeah, let's try that.
Okay.
Perfect.
Here we go.
Thank
All
you,
right.
Steph.
Sorry for the slow start, but now everything is working. Yeah, thanks again for the kind introduction again. And what I'm gonna do is, and I'm actually very grateful for the question that came up just at the end of Daniel's talk, because this will directly lead into what I'm going to talk here. So I'm going to focus on machine learning methods for MR acquisition and reconstruction. I kind of skipped over the analysis when I saw that Daniel is speaking before me, because obviously he can cover this and has covered this already. And I'm gonna essentially tell you some of our experiences when using machine learning, in particular in this setting of reconstructing images from undersampled Fourier data, because I thought this is where you have a very, very strong connection to OCT. And I'm going to show you some of our success stories, but I'm also going to show you some, or share with you some words of caution and stories and some of the experiences that we had over the years where we found this works and here you have to be cautious. So I hope it's useful and creates material for a bit of discussion. Just to start out, I want to point out that this is a very collaborative work, and everything I'm going to show you is the result of collaboration of my group at NYU with Graz University of Technology, with Siemens, with Facebook AI research. So lots of people were involved in the results that I'm going to show you now. And since this is an OCT conference, not an MR conference, I just want to spend 1 or 2 minutes telling you what we actually measure in MR so that you can make the connection to your research project. And our signal source is the nuclear spin, which is essentially a quantum mechanical model for the angular momentum of the nucleus. So what it comes out is that you have a rotating charged particle which has a magnetic dipole moment, and that means that if you put it in an external magnetic field, it has a tendency to align itself with the field just in the same way as a compass needle in the Earth magnetic field. And that is the simple reason why we built this huge major engineering project, $1 million machines that, just because this gives us our MR signal. This is a simple reason. And what happens is if we bring these hydrogen atoms in this magnetic field, they undergo this very, very characteristic motion that's called precession, and it's the same motion as a spinning top has in a gravitational field. And the important thing is that this precession frequency is very characteristic and linearly depends on the magnetic field strength. And we use this information to do the spatial encoding of our signal. And in particular, what we're doing is we are turning magnetic gradient fields on and off during the data acquisition, and we are encoding the spatial position of our spins in the frequency and phase of our signals. And this is the basic reason why we have this Fourier data, and I understand that it's very, very similar to the type of data that you have in OCT, but just to give you a little bit of a background, how it works in MRI and why we end up with this type of data. So the challenge we have with this basic physics type of not restriction, but just the nature how we acquired the data this way is that we need to repeat our acquisition many, many times to actually be able to encode an image. So we are exciting our spins, we are reading out a line in K-space, we need to wait a little bit to let the spin system relax, we need to excite again and do this over and over again, and then to build up our Fourier space. The problem is that this makes our acquisition very, very slow in comparison to CT or X-ray, where you essentially push a button and you have an image. So we usually take tens of minutes, and for some clinical exams up to half an hour to actually be able to get our protocols in place. And this has lots of problems because we struggle with patient comfort and compliance, especially with elderly or on one hand, or very, very young patients on the other hand. It makes MR a very, very costly acquisition or modality. We have problems with motion artifacts. If our patients cannot hold still during the scan, there is all types of problems that make our images essentially unusable. And there are also situations where we have time-resolved acquisitions where we simply cannot spend half an hour if we want to measure the beating heart in real time. So accelerating the MR scan speed has been a long-lasting research endeavor in our field ever since its invention. So one of the things that you can do to speed up the acquisition is simply to acquire less data. Let's say you only measure half of the case space and then do an inverse Fourier transform. Well, it does work. Of course, you have now reduced the scan time by a factor of 2, but you end up with an image that is corrupted by aliasing artifacts. So in a way, you have not really gained a lot. And this is where we started thinking about, can we use machine learning to obtain, let's say, the original image, even though we have acquired less data. And the idea is actually very, very simple. So if you assume that you have pairs of images available, where you have a fully sampled ground truth reference on one hand, and the accelerated acquisition on the other hand, can you then learn which of these image features are the original true image features and what is corruption that comes from aliasing? Because I actually know, and I can systematically reproduce from my fully sampled reference how the corruption will look like. I have complete control over the physical model that governs the acquisition, and I can simulate it in forward to retrospectively corrupt my images. So if you do this, then you end up with a framework that on a high level looks like this. You start out with your undersampled case-based data and some additional calibration information about the scanner that you can put into some kind of reconstruction model, which is a neural network, and it has some parameters. Details are not so important at this stage. But this model then will give us some type of reconstruction, and in the beginning it may not be particularly good because we haven't trained it. We compare it to some kind of reference with a similarity measure, and that could be as simple as the pixel-wise difference of the ground truth reference to my reconstruction. And then I'm updating the parameters of this neural network so that this error between the current reconstruction and the reference is minimized. And then you just do this for all the examples that you have in your data set, loop over the examples that you have, adapt the parameters accordingly, and then thereby train your model to give you a reconstruction that is as close as possible to the ground truth. And this was really interesting to watch in the field. So we first presented this at the ISMRM conference in 2016. And at that time, there were a total of 3 presentations that did something along these lines. There was one from China, one from Korea, and ours. And ours was actually in the 8 o'clock session at the very last day of the conference. So you can imagine how many people were actually there. But then the next year, this happened. So suddenly there were, I think, more than 50 presentations on this particular topic. They had to do entire sessions for all of this. The year after that, ISMRM did not organize only 1, but 2 conferences dedicated to machine learning. Mikai started doing workshops. This is now 3 in a row already. The 4th is currently being organized. And new papers are essentially coming out every single day. So this area has really, really taken off in our field. And just to give you a little bit more details how we approach it. I mean, this is really lots of approaches out in the field, but what I have always liked are approaches that combine the imaging physics with machine learning. So essentially you are solving an optimization problem where you have a term here that describes the mapping of the data that you actually acquire, it's denoted by F here, and the image that you are trying to reconstruct you. And you are putting all the information about your imaging systems, the knowledge, how do I scan my Fourier trajectory, how do my receive coil sensitivities of the system look like. You put that in there and you make sure that your reconstruction is consistent with this data that you acquired. And then you have a term here that is the actual learning part that really is there to identify what is the structure of my aliasing artifacts and what is the structure of my original image. And that approach allows you to get away with using a smaller number of model parameters because you're not spending model capacity trying to learn the imaging physics. And there was a question about training data available. We never have enough training data. In particular, in medical imaging, we simply don't have millions of data sets available. So if I can insert some of my knowledge and get away with using a slightly smaller model and therefore using less training data, this is what I personally always choose to do. But I would like to point out that this is an open debate in the field at the moment. There are some people who really want to say, let's learn everything end to end and don't care about any of the physics, and we can learn everything from data, and others are more cautious and others are in between. So this is really exciting to see what's happening there. And I would guess that in the end, it depends on the application. There are benefits, pros and cons of each of these approaches. So what you then need to do is you need to solve this particular optimization problem. And I don't know how you do it in OCT, but in MR, we usually use iterative gradient descent based methods to solve these type of optimization problems. So essentially you need to come up with a series of gradient descent steps, and you now need to map this onto a neural network. So essentially every layer of your neural network needs to perform a gradient descent step. And if you have a differentiable model, then you essentially can write out this gradient and build a neural network architecture that does exactly this, where every layer in the network does exactly this update step that I've written here. And you can sketch this out, and that essentially then becomes the design criterion of your network, where you put in the case-based data on one end and get out the reconstructed image on the other one. Yeah, and then when you put your raw data through the network, then you can observe how the images look like as they are being passed through the network. And it's kind of interesting. So you start to see that you lose this very classic monotonic behavior where the image gets better and better with every iteration step. It actually oscillates back and forth because we don't really impose any constraints on what happens inside the network. All the network cares about is getting as close to the ground truth at the very, very end, and it's free to do whatever it wants to arrive at this stage. But it can give you interesting debug information. Just showing you some of the examples that we got. This was from our first paper on knee MRI, where we compared the machine learning approach against compressed sensing, parallel imaging, which was the state of art in research before the machine learning methods were introduced. And what really pleased us to see was that we had really nice performance in terms of removing these Fourier aliasing artifacts. They're outlined with these red arrows here, while at the same time preserving fine image features and the subtle texture of the bone in this case. And just zooming in here a little bit, so this is an example where there's actually pathology in there, and it's very, very subtle, just a couple of pixel wide, cartilage defect, and it's actually preserved really, really well in the machine learning reconstruction. This was confirmed by multiple other sites later. So this is an example from Stanford where they used deep learning reconstruction, similar type of approach to what we did for knee imaging, for abdominal imaging. And they essentially got the same results, that they had much sharper images, better predictability of small image features, while at the same time not introducing any type of aliasing artifacts in comparison to compressed sensing. The nice thing about this type of approach is that you can actually apply it very easily to other modalities. So in your case, it's OCT, but we tried it with CT. because you can simply exchange the model that describes the imaging physics from, let's say, the MR Fourier transform to CT sinogram projections. And then you can just use the exact same model, just change the training data. And this is the case for low dose CT, where in the bottom row, you see a quarter dose acquisition, and which essentially comparable image quality to the full dose exam. This is one example, just as a little bit of an outlook to show you that it does actually pay off to really think about what type of problem do I want to solve. So this is a dynamic acquisition where we want to measure the uptake of contrast agent in our tissue. And what I have shown you here in the comparison is on the left is just the traditional reconstruction. In the middle is a network with a design for static images, like the same we used for the knee. And on the far right, you see an image, a reconstruction from a network that is specifically designed as a 2D plus time architecture. So it really learns this temporal nature of the data, and you can see how much it actually pays off to adapt your model architecture to the problem you really want to solve. And then just a little bit of an outlook, an open question that you can then ask is, in this type of cases, what is my ground truth, right? Do I really care about how the images look like, or am I interested in really measuring the quantitative information? And this then gets into the question of what is really a good image in medical imaging. And we can discuss a lot about this, but it's in many cases, it's not the image that looks pretty, but it's the image that contains the most important diagnostic information. And especially with perfusion imaging, this is very, very tricky, because the network can actually learn to remove all the dynamic information, give you a static image that looks great, but then you have lost everything. So these images are really, really hard to evaluate based on, do they give you the information or not? So this is an ongoing problem that we have. We are currently studying this by doing mapping of kinetic, pharmacokinetic models after the image reconstruction, and then try to compare how, on a really quantitative level, how accurate are our results. And the other thing, similar to what Daniel pointed out in the end of his talk, is we are then putting these images into a classifier to try to classify between benign and malignant breast tumors, and then essentially try to evaluate our reconstruction based on which images give us the best ability to do a successful classification within your network. And then everything becomes quantitative, and you can put it together. One thing that I wanted to highlight, and this is something that did cause some issues in our entire field, and if the OCT community may experience something similar, we, when these first papers came out, had really problems with reproducibility. So just showing you a couple of screenshots from papers where you see people report results where they trained the model from 10 patients or a volunteer or 27 patients. And if every group uses their data to train their model, reports the results on their data, then it's really, really hard as an outsider, if you read all these papers, to put things into context. Because if the data is not published and not available, then you really have no idea how hard was the problem that they were trying to solve. Is the benefit that they are reporting coming from the quality of their data, or from the innovations in the model, or the machine learning training that was described? So this was really, really hard to evaluate for a number of years in our community. So one thing that we have been doing a lot, and I spent a lot of time at NYU to really just get data together that we can then share with the research community. And so the first attempt was, since we had this knee data available from the project, we decided to share it with the research community. We made about 1,400 clinical cases with raw data available for download. The link is here. You can just go to the webpage and download it. No need for any type of research proposal or anything. And then the year after that, we did a second data set with brain data, about 7,000 cases. And also these are available for free for the research community to use them as public benchmarks and design their algorithms with them. And then we also organized reconstruction challenges. So essentially giving the data out to the community, they train their model with it, and then we hold back some challenge data and then give this to participants only for a limited amount of time. They reconstruct this data and send us back and we evaluate them. So essentially, this is the workflow. Participants get the undersampled data. They send us the reconstruction. We calculate an error that goes on a web page, and then we select the top participants and send them to actual clinical radiologists for evaluation, and that decides the winner. And I want to show you a couple of examples that I found insightful, that we learned some really, really interesting lessons. So this is the result of one of the tracks of the 2019 challenge, and you can see the top 4 competitors there, or essentially the winners of the challenge. And on the far right, what you can see is a parallel imaging compressed sensing reconstruction that I did for reference after the conclusion of the challenge. And I knew the ground truth, so I tried my best to get as close as possible to the ground truth and doing an inverse crime, essentially. And you can see the amount of improvement that every single one of these participants has over my reconstruction. Essentially, they blew my approach away. There's not even a comparison. And this is a very, very highly accelerated result. So this is very impressive that across the board, multiple groups, I think the improvement over the state of the art before machine learning is very, very obvious. Where it becomes a little bit tricky is that in this particular case, there is pathology in there, and it's a meniscal tear. And you can see that it is actually not visible very well in the machine learning reconstructions. So that is not an issue per se of the machine learning reconstructions, because as you can see in the parallel imaging compressed sensing reference, it's completely gone as well. It is simply removed from the data. You simply have not measured enough data. But where it gets tricky is a little bit is that if you look at the image on the far right and you show this to a radiologist, no radiologist would make a diagnosis based on this. They would immediately say, yeah, something is completely wrong, you need to redo the exam. But the machine learning models are so powerful that they can actually give you images that look quite reasonable. So essentially, they might give you a much better confidence in what the quality of your data is, because the models are so powerful, but then some information might be lost. And this is another example of another type of problem that can happen, and this is hallucinations. So these are artifacts that were actually introduced by the machine learning models that can look conspicuously like image features. So in this particular case, this structure here looks like a blood vessel. You have areas where just aliasing artifacts are introduced that look like anatomical features. And it is very, very hard. I mean, I have shown these images to clinical neuroradiologists, and they cannot detect that these are imaging artifacts. And that then becomes a problem. And we have trained this systematically, and the take-home message, I think, is simply don't get greedy. So this is an example where the ground truth reconstruction is made up of 250 phase encoding lines. And this is what you get when you only take 128 lines, essentially half of it. On the top, the machine learning reconstruction. On the bottom, conventional zero filling reconstruction. And you can see that you can go up to actually a fair amount of acceleration, more than a factor of 10, and really get high quality images with the machine learning reconstruction. And there is a huge abnormality here, this tumor, and it's very, very well preserved, while the regular reconstruction on the bottom really deteriorates. What is interesting is if you push it further. And for example, with only 11 case baselines, you really don't get anything that even resembles a brain anymore with the conventional reconstruction. But with the machine learning reconstruction, you still get a fairly impressive looking brain images, but the pathology is gone. And you can really push this forward down to just 3 case baselines, and it shows you how powerful these models actually are. And I would argue that, I mean, if you compare the image on the far right to having no image available at all, it is still useful. You see that it's a brain and something is wrong in the bottom. But you have to be very careful with the amount of trust that if you're a clinician interpreting this image, you need to know the context of what type of information can I get from an acquisition like this, and what can I not deduct. So you cannot expect that this has the same type of image quality than your regular 3 Tesla 20-minute scan. Just same, showing that this is actually independent of the image contrast. Couple of things that we are working on at the moment in this direction. One is uncertainty estimation. So we are working on models that do a stochastic reconstruction, where you, instead of just a single image, you get an ensemble of models and images, and you can then get mean and standard deviations. So essentially, this allows you to generate maps where you can see spatially in which areas is the model very, very certain, and there is less uncertainty coming from the data, and where are areas where the variance is higher. And essentially, the model needs to make up for the lack of data by potentially inventing structure. So this could be, or the way I envision this that a clinician could be presented with the image and the uncertainty map. So if they see something suspicious in an area where the uncertainty is very, very low, then they would probably be very, very confident, saying, yeah, there is an issue here. But if this happens in an area where the uncertainty is very, very high, then they might say, okay, let's go back, let's do another exam, or just, yeah, get this patient back. Another technique that you can do, and Daniel already mentioned it, to study the performance of your method is adversarial attacks. So essentially, after the model you can have is trained, you can optimize to perturb the input to give you the worst possible result that is available. So essentially, you are getting a little bit of a bound, or it's not really a bound actually, it could be worse, but you get a bit of an idea how your model can fail and how it will react when it will fail. So there's a really interesting PNAS paper that came out. So if you're interested in this, I recommend that you take a look at it.
Florian, we're running a little bit late on time.
Yes, it's actually, I'm already done. So I hope I could give you a bit of an overview of machine learning for MR image reconstruction, get a bit of an idea of this idea of combining physics and machine learning, and I was able to make you aware of some of the pitfalls that we have in applying this technology clinically, and what we can do both on the basic science and on the clinical side to evaluate and move the technology forward.
Super, thank you very much. I think we need to keep the question and answer session very brief because of time, but there was one question that occurred up on the Q&A board there too. In the case of the reconstruction with just 3 lines, and the algorithm showing up an image, so naively to a non-expert in the machine learning methods, is that just a matter of the algorithm identifying features in the sparse data set and then going to the training set and pulling an image that then closely resembles that and throwing it up?
You get an interpolation of the training data that most closely matches some of the features.
I see. Okay, so it is an interpolation.
And that is the reason why pathology is gone, because essentially what you get is kind of like an average brain.
Yeah. How is uncertainty quantified?
Well, I mean, what we are, we just wrote the first paper on this. I mean, if you do this type of standard deviation or variance map of your reconstruction, that you could just sum over this and get with one scalar number that gives you a quantitative estimation of uncertainty of this particular model. But this is in very, very early stages, and I'm not sure how useful this will be, or if people will pick this up. It's just an idea.
Yeah. And then just one final quick question. The fact that you put together a repository of data is, I think, a great resource for the community. For others that may be interested in doing a similar thing for OCT, one question was, is that data that was obtained purely in NYU, or is it from multiple institutions, and were there regulatory issues associated with making that data publicly available?
Our data is just from NYU. We had discussions with other groups, but this is again in early stages. The biggest issue regulatory that we had is that this is clinical patient data. So one thing, for example, for the brain images we had to do is cut off everything below the eyes to make sure that they can no longer be identified.
Yeah.
But other than that, it was just a matter of going through NYU's legal department with data sharing, and it was actually fairly smooth.
Great. Well, thank you again very much. That was an excellent talk, and we really appreciate your participation. So and Florian, please also join us in the break session, if you will, because I'm sure that there were many other questions that we didn't have time to address. So for our third and final speaker for our opening session this morning, we're pleased to introduce Nishant Mohan, who is right now the Chief Technology and Product Officer for a company called Photonicare in Durham, North Carolina. Nishant did his PhD in biomedical engineering here in Boston at the Boston University. Did a postdoc as a fellow at the MGH and Harvard Medical School. Immediately after that, he was a senior optical engineer for a time at Bausch & Lomb, and then spent a total of nearly 7 years with Wasatch Photonics, ending as the vice president of their OCT division. In his current company, Photonicare, the company has developed the first FDA-approved OCT-based imaging device for middle ear diagnosis, and the focus there is on providing a quantitative assessment of potential inner ear infections. So Nishant, thank you for joining us.
Thank you so much, Brad. And it's a pleasure to be presenting at this conference. I mean, it's an amazing endeavor from you and your team. And I'm a little nervous because, you know, you guys are my old mentors. So it's a big honor to be presenting here. I'll start sharing the screen. I think I needed to redo the window. Okay, you guys can see it now?
Perfect.
Okay, awesome. Let's see. Cool. Alrighty, so my talk would be a little bit of an overview of machine learning and some of its applications in optical coherence tomography. I will not so much go into my direct research. I'm grateful for other speakers who gave us very good idea, and I'll touch a little bit on the history of machine learning and AI techniques and what we can learn from them, and maybe where a little bit of future looks. So some of you are coming from machine learning background and probably haven't heard so much about OCT. It's an amazing three-dimensional imaging technique which gives us subsurface information, very highly used in ophthalmology, and has strong potential in a lot of other medical imaging domains as well. Machine learning, it's, I would say a general definition is ability of computers or devices to learn from data, and a lot of people believe to produce some human-like output. So the power comes from the fact that the computers can learn from input and output sets, and then you give them unseen data and they produce the expected output. a very powerful technique, and we will see why it has grown so much lately. So in this presentation, I will talk about some of the drivers behind the growth in machine learning-based techniques. What are some key categories of applications in OCT? I won't say it will be comprehensive, but I will try to cover the key areas which I see where it's applicable. Some of the key concepts in deep learning, which has been driving the growth in machine learning lately. What are some practical considerations, especially from, you know, like an industrial and commercial perspective? What does it take to bring a machine learning or a deep learning based system to the market? That will be extended into what are some regulatory implications of using machine learning based methods in medical imaging. So let's jump in. So we are living in a time of artificial intelligence and machine learning boom. No matter what metric you look at, things have been growing at an exponential pace, whether it's number of startups or the investment dollars or the job openings or the number of patents, the publications. Everywhere we hear about artificial intelligence and machine learning, and of course, AI Index is a great resource. You guys should check it out. It kind of covers all these. And like, how did this all start and what has been driving it? I think there's some key questions to ask that really helps us know where the field is going and how it can be useful for us in OCT. I think so. The fundamental problem in medical imaging is related to computer vision. Computer vision can be broadly described an ability of computer to understand what is in the image, which means what are the contents, where are they located, and what is their relationship to each other. And that's really what vision comes down to. And in the in the traditional field of computer vision, they try to answer these questions which extend directly to medical imaging. We always want to know what is in the image. Is there a pathology or is there not? If it is, where is it present? And how does it relate to other things present in the image? In traditional computer vision, there is a massive data set called ImageNet, which has over 15 million labeled images in 20,000 different labels themselves. And there is a contest which used to happen every year, and we see what algorithms can predict what are the categories in the images and where are they located. So this contest till 2010, a human being, like an average person, will usually have a 5% error rate on these 14 million images, obviously with a small sample and these categories, whereas computers will have about 25% error rate. We kind of stayed around this number till 2011, and it's similar before that with some incremental improvement. But then a big switch happened in 2012 when the error rate suddenly dropped by about 10 percentage points, and that's massive. And this was an algorithm from University of Toronto called AlexNet, which used an 8-layer neural network using GPUs to train it. And I'm sure many of you have heard of AlexNet. Very different variations of that. It are often used in classification problems. And that kind of set the stage for neural network-based machine learning to really take off. In 2013, a company called Clarify, I think coming from Columbia University, had improvements on that. Then by 2014, big players were jumping in it. Google came up with a 32-layer network, GoogleNet, that showed 7%. It should be 7% error rate. And then in 2015, Microsoft Research Asia had a 152-layer neural network, and that had a accuracy, but this should again the error rate less than that of a human. So the machine was able to tell what is in the image better than what an average human being can. And things kind of kept taking off from there. And I think by 2017 and 18, I don't think we have the contest anymore. So that showed how the field of computer vision has suddenly has had such major breakthroughs, and mostly driven by machine learning methods. And what, in my view, has been driving this is threefold. Number one is algorithms. They're all neural network based. Neural networks have existed since late 50s with the invention of perceptron, I think at Cornell. And what has changed is we have learned ability to train and work with very deep neural networks. That is, neural networks that have a bunch of different elements. And this has been supported by availability of a lot of data. We often hear about it, like once you have a lot of data, your machine learning will do better. I think there were questions asked in the session, like how much data we need, and the answer usually is more the better. And the reason for that is until we had capability of very deep networks, data wasn't that important, because after a while, the performance saturates because you have only that many variables you can train on. Once we have ability to have a deeper neural network with more variables, then this increasing amount of data started becoming much more useful, and this power of neural networks with data became more important. The third factor has been hardware, primarily driven by growth in GPUs, which were obviously not invented for scientific research. They were for gaming and display purposes, but their capability to do parallel processing has been a great boon for neural networks as well, because neural networks can be trained in parallel, and they actually are considered to be what is called an embarrassingly parallel problem, because it's very easy to do parallel processing for training of these neural networks and sometimes inference as well. So these three factors have really given a new life to the field, and we are seeing constant growth in applications. We hear things everywhere, but I think it's important to be aware of what is driving it, so we kind of have some context. Now, coming to what can it do for OCT, we see publications on, I think I have, if you have Google Scholar alert for deep learning in OCT, there's papers showing up every day, every week. I think they fall in three main categories. I don't call this comprehensive, but I think it covers quite a bit. Number one is segmentation. Number two is classification, and number three is enhancement or reconstruction. And some of our speakers with MR background talked about that as well. I think folks in OCT field understand these things. Segmentation is always an important problem in OCT, whether we are looking at retinal layers or trying to get the diameter of lumen. Classification, again, relates often to pathology, presence of pathology or not. An argument can often be made that a segmentation is a classification problem as well, because segmentation is nothing but classifying different pixels into different categories, which we expect in the image. And then there is aspect of enhancement, as we saw in some of the earlier talks, like you take an image which is considered to be lower quality because it was taken faster or with different kind of instrumentation, and can we train the network to give us an enhanced version of it? We won't go into full literature survey of it, but a lot of work has been done. One classic paper that comes to mind is from DeepMind, which talked about the clinically applicable deep learning for diagnosis and retinal diseases. And it kind of covers both the segmentation and classification aspect of machine learning. So they, the goal is, can we present OCT data to the computer, and can it make the referral calls? Should the patient be seeing an expert or should they not? What are the potential diagnoses? And the approach the team took there was to, they first did the segmentation part. So they took 800 images for training data set and created a network which could segment the OCT images into different layers. Now they took these segmented maps and presented them and labeled them with the appropriate referral as well as diagnosis labels. So is it urgent? Is it semi-urgent? Nothing to worry, observation? And what are different pathological conditions? The right column here denotes the probability. So they used 15,000 such maps, which were automatically segmented to then make the call regarding the action to take. And some of the categories were the presence of artifacts in the images, even blinks, etc. So very useful on what image is usable versus what is not. And let's look at the results which they obtained. So we want to see what is the error rate of humans versus machines. So when you are only presented OCT data and the human experts were compared to the the consensus outcome, we see that, based on the experience of the specialist, there was a different level of performance. Optometrists who often don't see a lot of retinal OCT have more mischaracterizations compared to retina specialists. Including fundus images in it improved the performance of both the optometrists and to some degree retina specialists as well. When we compared to the machine performance, it actually outperformed most of the specialists, or was equal to the best of them. So this, that obviously the paper had a huge impact on the field, and I consider it a good demonstration of use of segmentation and classification techniques in OCT using deep learning models. So the other aspect is of image enhancement, and we will step out of OCT and look at this. I consider to be a really nice paper on how to enhance images. It's called Learning to See in Dark from Urbana-Champagne in collaboration with Intel Labs. And what they're trying to do here, they have this image. This is almost, we cannot see with our eye on anything on it, and it is taken with an ISO level of 8,000 on the camera. And we know from our iPhones and Android phones, you increase the ISO level, you can get some signal, you can see something in dark, but the noise is higher. So the idea was, can we use this image as input to the training net, this as the output, train the neural network, and then generate the final output for the unseen images using this setting. So you are in, you're in very dark settings, you still keep the noise level low, and can you get the output from here? And the answer is yes. They had really good performance on this. They used a unit. They used multiple models, kind of converge towards unit in that. So this kind of lays the groundwork for a lot of medical imaging based techniques, which can use similar idea where you don't have enough time to do long integration or averaging. Can we get high quality data just from single samples? And this has been demonstrated in OCT as well. There's Devala and others who showed it for optic nerve. You can see this is a single frame. This is the average frame, and this is denoised using machine learning. I think they used a unit-based model as well. And you can, with the same acquisition time, you can get similar quality images as if you were averaging. Same here with goal of speckle reduction in this paper, which looked at more of the retinal areas, including optic nerve and fovea. In my previous work, we have tried similar ideas on using, you take a noisy image, you want to keep your integration time low for avoiding patient motion and fringe washout, and then apply a deep learning model. This was again unit-based with skip connections, so it has a ResNet and unit combined, and you can get a higher quality image starting from a more noisier image. So I think these are the kind of three categories which have been impactful in OCT. Then just to give a quick introduction for folks who are maybe new to machine learning, that most of these networks are based on what are called convolutional neural networks. Convolution is mathematically basically taking a filter set which you apply to your original image. The image is represented as pixels, which each pixel has a value which represents whether it's dark or white. So 255 is bright and zeros are very dark. The mathematical operation relates to multiplying the numbers and adding them together. And then we move this filter, which is multiplying and adding throughout the image. And we get different results doing this. Once we apply to it the entire image, we can get the kind of effect which we want. Say for, in this case, this was edge detection. So we can design a filter which detects edges and can convolve it with the image to get the necessary outcome. A convolutional neural network, what it does is it sets up a template of filters, but does not define initially what the values of those filters are. Then it takes an input image and provides the output answers to the model, and then lets the model train itself and come up with the right answers for these filter sets. So the whole idea about training and testing driven by filters. Another important concept here is to remember is that of pooling. Most of these networks use the concept of pooling, where they actually combine the output of some of the filters and pool them together to keep the size in check and provide the useful information from the previous layers. And most neural networks you see are combinations of these convolutional layers and pooling layers, and in some different fashion, with some other ideas of skip connections and dropouts, etc. Okay, and these are some of the famous networks. AlexNet, as we talked about before. VGGNet was a larger network which used the idea of using fixed size filters, so you can it's easier to train it. InceptionNet from Google used multiple size filters, where the training process itself decides what are the right filters to choose at different stages, as well as you can take output at different stages of a neural network itself. ResNet uses skip connections, helps you build very large neural networks. One of the big challenges in neural networks is how do you train a large network, and skip connections, which is basically skipping some of the filters if they're not necessary, has been very useful. And there are a few concepts. I won't go into detail of these in essence of time, but few things to remember while training deep networks is a concept of overfitting, which is you don't want to make a network too large if you don't have enough data, because then we are just defining a very complex equation to solve a problem where we don't have sufficient data for generalization. It's an important concept in any machine learning problem. Another important concept is data augmentation. Sometimes we may not have enough data, but we can create more data from existing data. And you've probably seen some of the presentations. We can crop, rotate, translate data, and that is still better than having no data, even though it's no new piece of information. And then transfer learning, I think some speakers talked about it, that we can have a network trained on some available data already, and then actually bring in the new data category and change only few layers. So that allows us to limit the amount of training we have to do when we have limited amount of data. So the fundamental problem of deep neural network always comes down to matching the training data to the complexity of the relationship between input and output. So if there's a more complex relationship, we will need more data, and vice versa, and how to manage the training of such networks. I will skip through details of these three categories. I think there are other speakers that will cover it in some detail, but I will jump to some of the practical issues in developing deep neural networks. So we mostly talk about the algorithms related to machine learning, but there is a lot more to it. And here's usually how the pipeline looks if you're trying to bring a machine learning model to the market. You have to do data collection, you have to label that data, you have to develop the algorithms, we have to deploy them, which is very important. Like you can't just develop the algorithms on a massive server and expect it then to work in the field on a cell phone. And then as most of OCT is in medical imaging, we have to look at the regulatory approval process. These data collection and data labeling probably are one of the most time-consuming things and are a backbone of machine learning, but they're often not talked about a lot. And if you're doing actual machine learning, this is where most of the time will be spent. Algorithm development is the most popular, it's the fanciest, and something which is most often looked at. And we will mostly be focusing on that. Another very important one is deployment. Is like once you have developed a machine learning model, how do you actually make sure it works with everything else? So it is in an OCT machine. The machine is capturing the image. It's doing a lot of other things. It has limited processing power. If we want real-time output, how does it fit in with the rest of the processing hardware, software architectures? And this is mostly a very non-trivial problem. And this is where the rubber hits the road, and we face a lot of practical challenges. There have been developments. I'm sure people have heard of TensorFlow, the most common platform for implementing machine learning algorithms. TensorFlow Lite actually is a version which can run on devices which have less computational problem for, like standalone devices or mobile applications, etc. And then the last one is regulatory process for bringing machine learning methods to market. And this is a very unique challenge because, you know, for regulatory purposes, we want something which is well tested, completely closed in, and then we want to take it to the market so there is no ambiguity in terms of safety and efficacy. However, machine learning methods by definition are evolving. So how do we regulate them? There is a study guide or like a guideline paper which came from FDA recently, and that kind of gives a very good introduction. I will cover some aspect of it. One is to understand the severity of the condition which we are working with and the significance of the information. So if the severity is critical and the significance is to treat or diagnose, that means it's a very important piece of information. We have to be extra careful. If the severity is low and it is just informing some clinical management, then the challenge is the risk to the patient is much less, and we can potentially be more adaptive there. There are four. There's a little article from which I wrote, which is it's taken from. There are four key things to pay attention to as we go through this process. One is to focus on good machine learning practices, and this is something which, you know, every group doing machine learning should focus on. Some of the previous speakers talked about it. To, you know, make sure you are protecting the privacy. Your data is representative of the population you are working on, and all the other necessary things, so we develop the right algorithms. A very important concept is to make sure that we define the change protocols before we take the device for approval. So we know it will change, but we will try to define in advance how it will change and what testing will need to be done to make sure the changes have not caused any new issues. And then once it is in the market, we make sure we constantly monitor it and understand its implications. So in short, the regulatory approach to machine learning methods will be different moving forward, and the community will have to adopt and follow good practices, so both the regulators and the users are happy with it. So before closing, I talked about all of them. Before closing, I kind of wanted to leave with a sign of caution and warning on how much machine learning and artificial intelligence is used in general vernacular these days. So here is a quote, which from some experts in artificial intelligence, which said, in spite of all the commercial hustle and bustle around AI these days, there is a mood that I'm sure many of you are familiar with in deep learning, familiar with of deep unease among AI researchers who have been around more than the last 4 years or so. This unease is due to the worry that perhaps expectations about AI are too high, and this will eventually result in disaster. And this is not a quote from, you know, our last conference I went to. This is a quote from 1984. And this, you know, the boom in artificial intelligence or machine learning or whatever level we go with has been there before. And sometimes the amazing results raise the expectations too high, and people start believing we can do literally anything with these methods, and that's not true. The physics still stays as always. So we should be careful both pedagogically as well as in expectations which are being set on what these methods can do. So in summary, there have been significant developments in AI and machine learning. The large data sets which are easier to acquire in OCT compared to some of the more complex imaging techniques like MRI-CT, I would say, make these methods even more suitable. We always have to pay attention to what will be practical challenges to bringing these algorithms to the market. And one thing from, again, from training perspectives, which I would suggest is still making sure that students and researchers are focused on the problem and not too overtaken by the glamour of machine learning methods themselves, because I often see these days new students are completely focused on machine learning and are not focusing on the basics of imaging and image processing itself, and that's not the right thing. So I will leave with that caution. So thank you so much.
Yeah, thank you, Nishan. I think that we are a little bit behind the schedule, but I'd like to have just a couple of questions. One thought that crossed my mind is after listening to Florian's talk, where his models incorporate the physics of underpinning MR and the actual RF data as well as the image data into as the inputs. A big concern I have in OCT is that none of the commercial systems, whether in ophthalmology, gastroenterology, or in cardiology, save the raw data. So the RF data is not available for input into these. So I think as a community, it's something that's really important. I mean, we now think that we have large data sets, which we do of images, but not of the raw data. One question that came up here in the chat was another practical issue is whether to use your own GPUs or to rent cloud computing time. Do you see any problems depending on only a few cloud providers?
Yeah, I mean, the few cloud providers are big players in the field. They provide these GPUs for a much lower cost. So far, it has been okay, but the questions of data privacy and security definitely come into picture when we are using external sources for such training and computation. So it's something to be aware of.
Another question was about the pre-processing of the OCT data prior to input to the training set for the neural nets.
So I don't know if the questioner mentions what kind of pre-processing.
I guess that's the question.
Oh, so the question is, should there be pre-processing done? That's actually an interesting question, and there have often been people who believe in purity of neural networks will say that there should be no pre-processing required because the network should be able to learn by itself. But then the question is that obviously demands a more complex network and larger data set. It does make sense that we can sometimes pre-process the data, which kind of lowers the burden on the network itself. Mm-hmm. And I think that if done correctly, that definitely makes sense.
Mm-hmm. Mm-hmm. And then one final question before we go to the break session. How do you see the growth of edge AI versus traditional systems?
Yeah, I mean, as you know, only that many systems can be desktop based. We are seeing so many, in the field of OCT itself and in so many other imaging technologies where the device is going to the patient rather than patient going to the device themselves. And that would mean that we will have to make sure that such algorithms can actually run on edge computing devices, and that's where the deployment challenges become very important.
Great. Well, thank you again, Nishant. And so for our audience, just a reminder that the break session is, we hope this is kind of an analog to the in-person coffee break time where you can walk out into the hall and have a chance to speak with people. We'll be in a separate session. So we'll adjourn this session and then go back into the sessions button, and you'll see a new session, which is the break. And I'll ask the speakers to join us there, and we'll allow people to join in with a video audio link and be able to ask questions and stimulate discussion. So thank you to all three of our speakers in this morning session. Thanks.
Thank you, Brett.